This video focuses on the fetch execute cycle, which is a fundamental part of how instructions are executed within inside the computer. This diagram represents the different parts of the processor and what is attached to the processor. We've got a series of registers here. One of these is called the program counter with the acronym PC. We've got the memory address register with the acronym MAR. We've got the memory buffer register with the acronym MBR, the current instruction register, the CIR, where each instruction is split into an opcode and an operand. We have the register known as the accumulator, the ALU, which is the arithmetic logic unit. And on this diagram we can see main memory. In main memory at the moment it's just highlighting one single instruction in main memory. We have the address bus showing one direction from part of the processor to main memory, and at the moment in this diagram this is showing the data bus, which is bringing this instruction back from main memory. Now do remember, the data bus carries data and instructions. The address bus is unidirectional, one way, and it is the processor that generates addresses that go on the address bus. So looking at where we started, the program counter has increased by 1, and so this indicates whereabouts the next instruction or data is located in main memory. The fetch part then. The contents of the program counter are transferred to the memory address register. If we look at the notation over here, the square brackets mean contents of. So the contents of the program counter are assigned to the memory address register. And we can see that there, the program counter currently has the binary for number 3. Inside that is transferred to the memory address register. The memory address register acts as like a buffer. It waits there to go on to the address bus, and that gets transferred to main memory. The next stage of the fetch execute cycle is the program counter being incremented by 1, and you're just able to see that happen there. So the program counter has now become 4, represented in binary 16 bits. So the contents of the program counter are incremented by 1, the contents was 3 plus 1, and that is assigned back to the program counter. The contents then of the addressed memory location, so let's have a look at the memory address register. Here, this is saying the binary equivalent of number 3, that is going on the address bus, so that is referencing position 3 in main memory. So the contents of this address are transferred along the data bus to the memory buffer register. So we can see that's just taken place there, and this is what it's saying here: the memory contents are transferred to the memory buffer register. The contents of the memory buffer register are then transferred to the current instruction register, and the current instruction register breaks down the instruction into an opcode and an operand. The opcode in this example is add. Remember, other opcodes might be load, store, add, sub for subtract. Other ones we've seen: LDA, STA, imp, out. The operand is what we perform the operation on. So once that is in the current instruction register, remember this is saying the contents of the memory buffer register are transferred to the current instruction register. At this point, the instruction is then decoded and executed, with the results of any execution temporarily being stored in the accumulator. So that is the fetch part of the fetch execute cycle. One note on the terminology. If we look at the notation again, we always refer to this with its acronyms. In an exam, you may be asked to describe this in words, you may be asked to fill in a missing line that's not there, or explain why this happens. So I'm just going to go through this one more time. The contents of the program counter are transferred to the memory address register. The contents of the program counter are incremented by 1 and placed back inside the program counter. At exactly the same time as this happening, this also happens. The contents of main memory that have been addressed is transferred to the memory buffer register. So you'll often see on the notation there is a semicolon between these two lines here, and that indicates that they both happen at the same time. They can happen at the same time because they are independent, they are using independent registers from each other. This one is using the program counter register, and this instruction is using the memory buffer register and the contents of memory. So that's just one thing to note with those two instructions. They can happen at the same time. So the contents of the addressed memory location, we need to add addressed in there, is transferred to the memory buffer register. The contents of the memory buffer register is transferred to the current instruction register. The current instruction is then decoded and executed. So here is that notation again. Now this is written the way that you will see this in the exam. The contents of the program counter are assigned to the memory address register. The program counter, the contents of it, is incremented by 1 and assigned to the program counter. At the same time, the addressed contents of memory is assigned to the memory buffer register. Then the contents of the memory buffer register is assigned to the current instruction register. The instruction is decoded. It is then executed. So from the diagram again, if we just look at the different registers, remember a register is a very small area of memory, it's very fast, and it is on the processor itself. Registers tend to be either general purpose registers or dedicated registers. The program counter, the accumulator, the current instruction register, the memory address register, the memory buffer register, these are dedicated registers. Two more that are not on the diagram are the status register, known as SR, and the stack pointer, known as SP. The status register, that holds condition codes to indicate the outcome of operations. For example, an arithmetic operation may produce a positive, a negative, 0 or overflow result. So the status register is a flag that indicates which of these it currently is. General purpose registers, they're available for the programmer to use, and they store data temporarily. They have not been assigned a specific role by the processor. General purpose registers are accessed with instructions such as the load, the store, the add. If we look now at the execute part of the fetch execute cycle, with the execute, the instruction is first decoded. So from the current instruction register, it takes the opcode, sends that through the instruction decoder to work out what that is. Remember, each operation code, opcode, is associated with a series of bits that indicate what that is, and this becomes the instruction set for that actual processor. Each processor has its own instruction set, which are all the instructions and the codes associated with them. So within this example, it works out that add operand to the accumulator. 0101 is add. The operand is the number 6, and we've got that here. So it's going to add 6 to the accumulator. The accumulator has currently got 4 in there, so we're going to execute that instruction. That goes to the arithmetic logic unit. It takes 6, adds 4, and the result is 10, and that is then stored back in the accumulator. So that is the end of the fetch execute cycle with that one instruction. What may happen next is a further instruction to store the contents of the accumulator. Again, the same process will happen. The program counter has got 4, so the contents of the program counter get assigned to the memory address register. The program counter is incremented by 1. The contents of the addressed memory location is transferred along the data bus to the memory buffer register. The contents of the memory buffer register is transferred to the current instruction register. That is the instruction being fetched. The opcode is decoded using the instruction decoder, and this is performed, the operation is performed on the accumulator. So that is the fetch execute cycle.